Hi everyone. Hopefully there are some of you around, and I'm very happy to have Karthik Suresh with me here today. And as promised earlier, we are going to catch up with the syllabus as much as possible and as and when possible. So today is another session on increasing and decreasing functions, what we discussed last time. But before I share my slides and get going, Karthik, step in and say hi to your friends. They may watch you later, maybe the recording. Some of them may join us as I have changed the event page maybe a little later. So, Karthik, how are you?
Hi everyone. I'm fine. Yeah, I'm excited to be here.
That's wonderful, fantastic. I'm so glad that you guys are volunteering to be part of this experiment, you can call it. But I think it helped when you saw last year's recording, so it helped. So maybe it will help you when you look back at all of these recordings later in the year. And of course, I'm looking forward to packing in a little more of the syllabus as well in this time, so that we are all at ease at a later time. To get started with, we are going back to our slides. So I'm going to just share my screen and get you going with our presentation that we were following last time. And here we have the increasing and decreasing function. So we are looking at starting off the slides with the idea of what increasing and decreasing functions are, and how do we make use of this idea in solving our problems. So a very quick look at what we discussed last time. This is one theorem, significant result, which is going to be used in every problem in this exercise. It says that if f is a continuous function on closed interval AB and differentiable on open interval AB, then f is increasing in closed interval AB if the derivative of f at every x belonging to open interval AB is greater than 0. We also saw the same thing happening with the help of the GeoGebra applet in the last session. So if you missed that, get back to it and check it out as to what we observed. The second condition is if f is given to be a function such that it is continuous on closed interval AB, differentiable on open interval AB, then f is decreasing in the closed interval AB if f dash of x is lesser than 0 for each x belonging to open interval AB. And the third condition sounds like an obvious case where we say f is a constant function in closed interval AB if derivative of f for every x belonging to open interval AB is 0. Now, with these three conditions, I have also now added in another result, which is given as a remark in your NCERT textbook, which says that if f is continuous on a closed interval AB and differentiable on open interval AB, then we are looking at these three conditions. So, Karthik, I would like you to just step in. I have to check out at the door, there's somebody. So, if you can just read out these three conditions, can you see the screen?
Yeah, now I can see it. I couldn't see it earlier.
Yeah, you can see now?
Yeah.
Just read out these three conditions and I'll be back in a minute.
So a function is increasing if first in order to check if it is increasing, it should be the function should be continuous on the closed interval a to b, and it should be differentiable on the open interval a to b. Then if the derivative of the function is turning out to be positive for each x belonging to open interval a to b, then we call it a increasing function. And if the derivative is negative, then we call it a decreasing function. And if a function will be increasing or decreasing in R if it is so in every interval of R.
Right. Now, the difference here in this result and the theorem is that we are talking about the difference or a slight distinction between strictly increasing and increasing. Strictly increasing is being referred to when we are looking at open interval AB. Whereas strictly only increasing, when we saw in the previous slide, the theorem said that we are looking at the function to be increasing in closed interval AB. So this is a distinction that is maintained in your NCERT textbook, and we will try to adhere to this notation as we go along. So strictly increasing in open interval AB, typically because the behavior at the endpoints of the interval is sometimes not known. You do not know how the function is going to behave because it's given to be only defined, and condition about continuity and differentiability is known only in this given interval only. That's its domain. Now, we did talk about questions of such kind where we were establishing that the function is finding intervals in which this function is increasing or decreasing. So these were polynomial functions that we focused on, and it was a very step-by-step method that we followed with the idea that this function, as we look at the derivative, is going to change its behavior at the points where the curve is going to turn. And at those points, which are turning points or stationary points, the derivative is 0. So we first evaluate the values of x for which f dash of x is 0. And for that, it helps if we can factorize the derivative that we have got. This particular example that we saw last time, it was a 4th degree function. Derivative is a cubic function. So you must know results that we had done in our previous classes. One of them known as the factor theorem, which helps us to factorize a polynomial. So it's a very essential technique that you must know, otherwise you can't proceed. And once, yeah. Were you saying something?
Yeah, the slide didn't change.
Slide didn't change?
No.
Did it now?
No, it didn't.
Okay, let me check. So I'll just check why that's happening, because we do have the whole idea to be set up with that only. So I'm using the same slide. Let's see. So is that showing anything now?
It just came and went off.
Now you can see all the results. This is the problem we are discussing now. Can you see the polynomial problem?
I can't see it here.
You can't see the polynomial problem?
No, I can't see. It's a blank screen.
It's very much showing on my screen, the polynomial problem. So there could be some issue on your end. That's what is showing on my screen. What is it showing on your screen? Blank?
Yeah, it's just yeah, it's blank.
That's strange. It's white or black? Blank.
It's a blank. It's your picture is coming.
But I'm sharing my screen, so it can't show my picture. Some issue today. Let me try resharing that and see if it works.
Yeah, now it's done.
Now it's all right. You can see the polynomial problem.
Yeah.
Okay, so we'll quickly go through this again. When we look at the polynomial function, the emphasis was that we must factorize the derivative so that we are able to find the critical or the turning points. So using the factor theorem, we get the factors of a cubic polynomial, and we put f dash of x equal to 0 to get the values of x at which possibly the function is going to turn. These points divide the domain for this function, the entire of the real line, into sub-intervals. And these are the intervals over which we discuss whether the derivative is greater than 0 or lesser than 0. So when you're looking at a situation, and in this case, you have three intervals, minus infinity to minus 2, then minus 2 to 1, and 1 to 3, and then 3 to infinity. So we look at interval minus infinity to minus 2, and we examine whether all of these three factors are positive or negative. So when you look at x lesser than negative 2, then examine the sign of all the three. In this case, all the three factors are negative. So the total sign of the derivative is negative, and hence the function is said to be a decreasing function. Now this becomes a mechanical process that you would follow for the other intervals as well. And once that's done, then we are ready to conclude whether the function is increasing or decreasing in a particular interval or intervals. Now, another interesting thing that such an information tells you is that it will enable us to draw a rough sketch of such functions. So with a little more coming in as we progress with the topic, you'll be able to see that a fourth degree function, which was beyond us as far as the rough sketch is concerned, will become possible. But right now, this is a picture from captured from GeoGebra. So you can see that the function is a decreasing function from minus infinity to minus 2. Turns at minus 2, starts increasing, then again comes down from x equal to 1, again turns, and after 3 it starts increasing. So when you think about increasing and decreasing functions, so as a polynomial function that we started with, this function is neither increasing nor decreasing in its entire interval, that is entire domain of the real numbers. But over sub-intervals, its behavior can be discussed. So that is something interesting that we will learn and gain from the idea of increasing and decreasing functions. Now, in addition to these polynomial functions, we also have trigonometric functions where the same exercise can be done. You can be asked to find intervals over which the function is increasing or decreasing, or given a function and an interval, as in this case, you have to show that the function is strictly increasing function on the given interval, and it's an open interval 3 pi by 8 to 7 pi by 8. When you type with the math type in these slides, the brackets look like a closed bracket, but it is not. It's just again a circular bracket. So it's an open interval that is given to us.
The slide hasn't come yet. It's not showing again.
There is some issue today.
Yeah, it's there now.
It's there?
Yeah.
Okay. So I'm just going on full screen only with that. So I don't think, is it there now?
It's not full screen. It's just normal.
I think there's a certain lag in when I do something and what it shows. So yeah, so is it now showing to you in full screen, the slides?
No, it's not in full screen. It's just the normal view.
Okay, we'll give it a minute. I think it's the video and the sound is not going along with it, perhaps. So if you, can you see now?
Not on full screen.
So because then you can see the entire solution because they're not animated there. Is that so?
Oh, yeah, it shows the entire.
Yeah, that is a drawback. So, well, we'll try to see if we can get that fixed up. So, but as of now, I guess that is how it looks like. So, I'm going to just give it one more try and see if I can fix it up. But Otherwise, we'll continue with it as it is. Doesn't matter. Right. So again, when we look at trigonometric functions, the procedure is going to be still the same. It doesn't change anything for us. We are going to be looking at the theorem or result that we discussed earlier, that the function is strictly increasing or decreasing depending on the sign of the derivative of the function. So given f of x equal to cos of 2x plus pi by 4, f of x is f dash of x, that is the derivative, can be easily evaluated. Now the discussion is basically on what kind of a sign does this function f dash x takes when x lies in the interval 3 pi by 8 to 7 pi by 8. So x is between 3 pi by 8 and 7 pi by 8. Where does 2x plus pi by 4 lies can easily be figured out. So as a linear inequality, if you multiply by 2 and then add pi by 4 all across, you will be able to see that the argument 2x plus pi by 4 lies between pi and 2 pi. So sine of 2x plus pi by 4 will be a negative quantity. And therefore, f dash of x will become positive. And that helps us to conclude and say that the function is a strictly increasing function on the interval given to us, that is 3 pi by 8 to 7 pi by 8. All right, so if you can tell me, Karthik, did it make sense to do something like this? Was there a point that was not too clear in the explanation? Any doubt here?
Oh, no. We just manipulate the thing and get the...
Right. So given the condition on x, you figure out what it would be the condition on 2x plus pi by 4. So some of you may not have to go through these intermediate steps, and you can quickly figure out where 2x plus pi by 4 is going to be. But an argument, a reasoning has to be given even if it's a 1 marker or a 4 marker question in the exam, as the case may be. All right, so we have another question, and I think Karthik can step in for me here on this question, which is again actually a solved example from NCERT. Right, Karthik, would you take over?
Yeah.
Right, perfect. Give it a go. And move the slides one by one. Can you see the question coming up?
No.
You can't see the question coming up?
No.
Okay, so do you think you can share your slides? Is that possible? Or
1 second, I'll just open that thing. Yeah, I could do that.
Yeah, so why don't you take over then? I'll stop my screen and we'll try to take you from there. So you can move on. You can take off the show now from this point to the next two questions. Yeah, see if you can share your screen.
That's the thing.
Yeah. The previous one.
Just 1 second.
No problem.
Is it showing up? No.
You have to share your screen. Go to the right.
Yeah, I shared it.
Uh-huh.
It's not showing up?
Mm-hmm.
Yeah. Is it coming?
Yes, yes, it's there.
It's coming, right?
Oh, it comes and then goes off. I don't know why it's happening today. Shall I try?
It's sharing right now.
Yeah, it's showing your alternate solution slide.
Oh,
So you just have to move up to the sixth slide. Yes, sixth one. Yes, that's the one. So I think the problem is coming when you go full screen, it
yeah.
shuts that out.
When I'm going full screen, it's shutting it. Yeah.
Yeah, that's where the problem is coming. So I guess you can just continue with the slide as it is. Don't play it.
Okay. Yeah. So it's visible now.
Yeah.
So the question says function is sine x plus cos x, and x belongs to x is greater than equal to 0 and less than equal to 2 pi. So there are 2 or 3 methods by which we can do this question. So the first one is we just differentiate the function, get cos x minus sin x, and then in order to obtain the turning points of the original function, or basically the intervals in which the domain gets divided, we equate it to 0. So which that will give us sin x is equal to cos x. And then we also know that sin x and cos x are equal only in the first and the third quadrant. So that will give us the value of x as pi by 4 and pi plus pi by 4, which is 5 pi by 4.
Right.
And then this gives us the set of intervals that is from 0 to pi by 4. Then open interval pi by 4 to 5 pi by 4. And then 5 pi by 4 to 2 pi, closed interval.
Right.
Did the next slide come up?
Yeah.
Yeah. So the now when we see it in the tabular form, we need to be just a little careful about which quadrant we are in order to assign the sign of the differentiated function. So between 0 and pi by 4, cos x is always greater than sin x, so that will give us a positive value. And between pi by 4 and pi by 2, sin x becomes greater than cos x, so that gives us a negative value between pi by 4 and pi by 2. And
Right.
then in pi by 2, between pi by 2 and pi, cos is always negative, so that will give us a negative value. And in the same way, between pi and pi by 4, we check which one is greater, and that gives us again a negative value. So overall between pi by 4 and 5 pi by 4, it gives us a negative value.
Right.
And similarly, we check it for the fourth quadrant as well, and that should give us a positive value.
Exactly.
So it's strictly increasing in the intervals 0 to pi by 4 and 5 pi by 4 to 2 pi, and it's decreasing in pi by 4 to 5 pi by 4.
Right. So again, as Karthik has explained, I think there is more discussion and observation involved in this method, especially when you take the pi by 4 to 5 pi by 4 interval. Because
Exactly.
the behavior of cos x and sin x varies as it crosses each of these quadrants. And here that is what is happening. So you need to be very careful in taking a call on whether the derivative is greater than or lesser than 0. Right. So you have an alternative method as well there. So would you like to explain that? Maybe that would become easier to have this kind of a discussion done.
Does it show?
Yeah.
Yeah. So in this method, what we do is we again differentiate and get cos x minus sin x, and then we multiply this entire expression by 1 by root 2, and then again multiply by root 2 to nullify the effect. And then that will become 1 by root 2 cos x minus 1 by root 2 sin x. And we can write this 1 by root 2 as sin pi by 4 and cos pi by 4. And then we can use the sin a minus b formula and condense it and write it as sine pi by 4 minus x multiplied by root 2.
Right.
And then we could also write it as sine x minus pi by 4, taking the negative sign out. That's not necessary, but we could do that. And we'll definitely equate it to 0 in order to obtain the points.
Right.
And then that could be written as root 2 sine pi by 4 minus x is equal to 0. And then using the general solution of sine, we'll get x as pi by 4 and 5 pi by 4.
Mm.
The general solution of sine is given by n pi plus minus 1 whole raised power n into alpha.
Yeah, here we are talking about sine theta equal to 0, so theta will be just n pi basically.
Yeah.
Right? And since x lies between 0 to 2 pi, there will be only two values which we got with that earlier method as well, pi by 4 and 5 pi
Right.
by 4.
Then we can see that x belongs to 0 to pi by 4. For that particular interval, we can write it as x is greater than equal to 0 and less than pi by 4. And then we manipulate this particular expression to get sine pi by 4 minus x times root 2. When we get that, we'll finally arrive at root 2 times sine pi by 4 minus x is greater than 0.
Yeah,
So,
I'll just correct that there, Karthik. Given x is greater than equal to 0, less than pi by 4, we check where does pi by 4 minus x lies. So that is coming out to be greater than 0 but lesser than equal to pi by 4. So this angle now lies again in the first quadrant, and
yeah.
therefore sine of pi by 4 minus x will be greater than 0, and hence root 2 times of sine pi by 4 minus x is greater than 0. That's what you meant there.
Yeah.
And that is what we were looking for to decide on the sign of f dash x, right?
Yeah.
Yeah.
One more thing which I thought could be done was that we from directly from f, in order to find which interval it is increasing in, we can say f dash of x is greater than 0.
Right.
And from there directly we can say root 2 sine pi by 4 minus x is greater than 0.
Yes.
And from there we can conclude that sine is positive in the first and the second quadrant. So in that particular interval, then from that method also we can come to this same conclusion.
Right, but then you will also have to be careful that from there you will also look at the other possible interval in which the derivative could be greater than 0. So it's not only 0 to pi by 4 interval that you will have to discuss. You will
Oh, yeah.
also look at the other quadrant in which this condition could be satisfied.
Yeah.
So x could lie between 0 to pi by 2 or pi by 2 to pi and so on. So you need to discuss all the possibilities, and from there, because the domain that is given to you of the function is 0 to 2 pi.
Yeah.
So with that condition in mind, that is where you will actually end up with two intervals over which the function is strictly increasing.
Oh, okay.
This is more mechanical because it gives you the breaking point. So you know these are the three intervals over which the discussion needs to be done. And if you only follow what you had suggested, you may miss out on another third interval which over which the function is needs to be discussed. That is the only catch. Otherwise, yes, you can do the discussion right at the step where you find f dash x and say
Yeah.
that f is strictly increasing if f dash x is greater than 0, and then
Yeah.
find the conditions on x from there. Perfect, absolutely. So there are multiple ways of doing a question of such kind. Right, that helps us definitely. Thank you so much, Karthik, for stepping in and taking over and bringing up a third alternative of the solution as well. And
Yeah.
I'll leave it completely to all of you, including you, Karthik, to decide what works best for you as a problem to be presented in a test or an exam. So that would be completely your call. So I think we are running into some technical problem today. So maybe if you can just quit sharing your screen, maybe we will quickly go through our next question, which is also a trigonometric function, and then we'll stop the session for today, and we will get back to this topic and chapter maybe the next time. Would that be perfectly fine with you?
Oh yeah.
Right. So I'll quickly now go back to sharing the slides from my end, and I will try to take you through the next question that we have, and Karthik will just quickly confirm whether you are able to see the screen or not.
Yeah, it's working fine now.
Slides are looking fine. I think
Yeah.
when I go full screen, does it still show?
No, then it goes off.
Then it goes off. Now that's something new for me, so I'll have to figure that out as to why that's happening. Okay, so I'm back to the entire solution is in front of you, but we'll still go, not entire, but half of it, but we'll go through it step by step again. Now the only difference in this question is that the function is a little more complex. So here the function is sine of x whole thing to the power 4 plus cos of x whole thing to the power 4. And we have to separate the interval 0 to pi by 2 into sub-intervals in which this function is increasing or decreasing. So not much changes. You start off with finding f dash x with the help of chain rule. And then if you just start thinking about where is f dash x going to be 0 with this um, look of it as of now, then it will be a very complex problem. But otherwise, if you just take a minute to sort this expression out, you will realize that it becomes a very easy task. Because if you pull 4 sine x cos x common, and you're left with sine square x minus cos square x, which is negative of cos square x minus sine square x. And this expression is nothing but cos 2x. 2 sine x cos x is sine 2x. So you have negative 2 sine 2x cos 2x, which is negative sine 4x. So f dash x becomes a very easy to manage function, and it's very easy to discuss its behavior. So for critical points, f dash of x is 0, which implies negative sine 4x is equal to 0. So 4x must be a multiple of pi. Since our condition is that x belongs to the closed interval 0 to pi by 2, so with that constraint, the solution for this condition would be that x is either 0 or pi by 4. And therefore, we end up with the two subintervals, 0 to pi by 4 and pi by 4 to pi by 2. So again, discussion of whether f dash x is greater than or lesser than 0 in these intervals becomes very trivial. When x is between 0 to pi by 4, 4x will be between 0 and when you take the multiple of x, it will be between 0 and pi. So sine 4x is positive. Therefore, negative of sine 4x is lesser than 0. So function becomes decreasing in the closed interval 0 to pi by 4, whereas in the intervals pi by 4 to pi by 2, it is increasing. And that is what was the requirement of the question. So the main trick in this problem is to factorize and try to simplify f dash x. Again, I was curious to see what this function looks like, because we have never plotted such intricate functions. So again, if you use a software, here it's GeoGebra, then this green curve represents sine x to the power 4 plus cos x to the power 4. And over its entire domain, it's neither increasing nor decreasing. And when you look at the interval 0 to pi by 2, it again changes its behavior at pi by 4. So from 0 to pi by 4, it's decreasing, and then pi by 4 to pi by 2, it is an increasing function. So that is something interesting, and it's something that you can do with the help of these softwares and technology. You can plot and see, and actually if you have the graph in front of you, then deciding whether a function is increasing or decreasing is really simple. But we don't have the luxury of doing that. So obviously we will have to go through this algorithmic way of checking, finding the intervals over which the function is increasing and decreasing. So I hope you are now equipped, those who are going to watch the recording later as well, are ready to try some more questions on trigonometric functions and deciding what are the intervals over which the given function is increasing or decreasing. That is a crucial part of your curriculum. So do find time to practice it, and we will take up the doubts when I see you all in month of July. So thank you so much, Karthik. Tell me, we did have a few technical issues today, but did you enjoy doing surfing through those and surviving through those issues?
Yeah, it was a good experience. Yeah.
Was it your first Hangout session, or have you done this earlier?
No, it's the first time I've done it.
Okay. For me, it's almost 10th session, but I've never faced these technical issues. So there is always a first time and new things to learn. So I'm going to figure out how to set them right next time I see these issues coming up. So thank you for joining me, and you have something important to take care of. So bye for now, and I'll see you all later. And this is a message to all of you who are going to watch this show. Please open up the textbooks, start preparing, catch up so that you are comfortable, ready to take on more in the month of July. So I'm going to try and pack in one more session or a pair of sessions next week before we see you in July. But till then, bye to everyone, and bye Karthik for joining me today.
Okay.